Is it April 20th or 21st? Can somebody check? It's 20th, right? Covers chapter 2, 3, and 4. So we did chapter 2 and 4 already. And we are going to finish chapter 3 very shortly. And the most important chapter of all is, of course, chapter 4, path regression. Okay? So I think everything that may be important, the most important one is the homework problem you're doing right now. So you have homework number 5, right? Is it number 5? So it has some exercises from the textbook, right? So that's a single most important piece for the exam. So spend enough time, make sure that you understand everything there. I'll tell you more about the coming exam a little bit later. If you go to the class website, you can find this document. The name is chapter 3, chapter3.pdf, okay? It has some summary of the chapter. So today, we are not going to do testing or confidence interval. We are going to do something even simpler than that. And my goal is to do first 2 pages of day 9 reading guide. Do you have the reading guide? If not, find it from the class website. In the first 2 pages, there are 4 examples. From example 1 to example 4. Okay? So the goal for today, I want to use the remaining 20 minutes to solve these 4 examples. Okay? This is something we did already. It's more like a repetition. I just want to formalize it. Before we do, let me just remind you of a few things. This is just terminology. There's an estimator and there's an estimate. So what's the difference? This is before you draw any sample. This is after you draw a sample. So what's the difference? An estimator is a random variable because this is before you draw any sample. You didn't actually observe anything, right? Anything can be possible. An estimate is after you draw your sample and observe its value. So this is just a number. There's no randomness left. So this is an example. I use a capital letter, right? So it means that it's a random variable. Here is a lowercase letter. It means that this is a number. So an estimator, like the sample mean, can be defined in this way, right? This is a sample mean of a sample of size 3. So I'm going to draw 3 from my population, randomly read replacement, and take the sample mean. This is before I draw anything. So y1 can take any values. It's a random variable. Once I draw a sample, and suppose that my sample happened to be like this, I draw 3 numbers, then sample mean is fixed, becomes a number. So that's an estimate. So typically, one important question from statistics is, if you have more than one estimator for the same thing, so for example, we like to estimate the population mean, and you have 2 estimators. Sample mean is one, sample median is another. The question is which one to use, which one is better, right? So that's a very typical question we have to find answer. So let me. So the 4 examples in this reading guide is about that. We need some kind of criteria, some kind of performance measure, so that we can choose one over the other. Okay. So the first criteria is the unbiasedness we did before, like yesterday. So what does it mean? An estimator depends on the sample. Different sample produce different value for the estimator. So an estimator has a distribution. Unbiased estimator means that the center of a distribution of an estimator must be equal to the parameter from the population. So center of the distribution must be the true value of something you want. So that's the meaning of unbiasedness. So how do you know that an estimator is unbiased? You just work out the distribution of an estimator, and then you can calculate the mean, the first moment. Okay. So a good estimator should be an unbiased estimator. Second criteria is consistency. What does it mean? You increase the sample size, the sample becomes bigger and bigger, eventually covers the population. So an estimator from the sample must be very close to truth, right? That's the consistency. A good estimator must be a consistent estimator. Otherwise, you have to think twice, right? You have to use something else. And there are many, many estimators that are unbiased and consistent. So how to choose? The third criteria is the efficiency. So it basically says that if you have two estimators, mu hat and mu tilde, and if they are unbiased and consistent, then we like to choose something that has smaller variance. Okay? Because from one sample to another, there's less variation. It is closer to the truth. In that sense, it's more informative. So if two estimators satisfy these two conditions, then we have to choose something that has smaller variance. Okay? So that's the meaning of efficiency. So this is the three criteria we are going to use. We can repeat this exercise for the regression, but for a while, let's just focus on the mean, unconditional mean. And let's consider three estimators. So can you take a look at this State 9 reading guide? This example 1. Again, the situation is you have a huge population. And you simply like to know the mean value of the population, so center of the population. It is unknown, so you're going to draw a sample. This is a sample. And using your sample, you can define an estimator, like the sample mean, or sample median, or some kind of weighted mean, like y tilde can be a weighted mean, or something else, right? And it depends on the sample. So a different sample produces a different sample mean. It has a distribution. So we have to check whether any of these estimator is first unbiased, second consistent, third efficient. Okay? So that's the point of this exercise. Now the first estimator looks like this. Anyway, the background is the sample must be IID. It has an identical distribution and they're independent. Because it has an identical distribution, mean and variance must be the same. Now the estimator we propose is so what does it do? Suppose that n is an even number, okay, like 10 or 20. Then what it suggests is, for the first observation, any odd number of observation, we give less weight. For any even observation, like second observation or fourth observation, we provide more weight. Okay? So the idea is that we don't treat each observation, we do not treat them equally. We treat them unequally. Some observations are more important than the other. Okay? So this is just one way to express that idea. So we can think about this kind of estimator for the population mean. So the first one is less important. Second observation is more important. You keep repeating things like that. So the question says, show two things. So the first claim is the center of the distribution of this y tilde, the weighted sample mean, is equal to the population mean. And the second claim is the variance of y tilde is equal to 1.25 times variance of the population divided by n. Okay, so that's two claims. So let me give you a few minutes, maybe 3 minutes, to try these two. So how do you do that? You just apply the law of expectation and law of variance. Okay? And just for the reminder, we did it before. So I think that we did it when n is equal to 3. The law of expectation says when you have a constant, you can put it out, right? And the expectation of sum of two random variables is sum of two expectations. They have identical distribution and they have the same mean. So we have 1 over n, which is the constant from here. So let's just put these two terms together. It's going to make 2 times the population mean. So how many of these combinations do you have? 2-term combinations do you have? N over 2. Right? So it canceled out. It's going to be the mu of y. Is it okay? So the first claim is true. So remember this. So in my case, I just erase a few things. In your case, you have to write the whole thing again, okay? So let's do the variance. So when you put out this 1 over n, what happens? You square it, right? So you square this and you change it to variance. You square this and you change it to variance. I like this. Is it okay? Okay, so let me rewrite it. Let me use the same trick. Let me put these two terms together. So we are going to think about this pair. If you add it as 10 over 4 or (5 over 2). Is it correct? Okay. Sigma squared, and we have n over 2 such pairs. Right? So you have this 1 over n and n canceled out. 5 over 4 sigma squared. That's why you have 1.25. Oh, no. What am I doing? There's no cancellation for n terms. Sorry about this. I was confused. So I have to keep this 1 over n squared, right? So one n will be cancelled, but there is another n left in the denominator. So that's the second claim. 1.25 sigma squared divided by n. Okay? If the sample size is big, the variance of your estimator is much smaller than the variance of just one observation from the population. So let me ask you this. Let's apply these 3 criteria and check our first estimator. Please tell me, is this y tilde, which is a weighted sample mean, is it an unbiased estimator? How do you know? The mean of the weighted mean, sample mean is equal to the population mean. That's the meaning of unbiasedness. So it's unbiased. Now, is it a consistent estimator? So when you know that your estimator is consistent, so one thing you can use is if the estimator is unbiased and if the variance goes to 0 as n increases, that estimator is a consistent estimator. Okay, again, the estimator is unbiased, the variance disappears, goes to 0 as you increase n, the sample size. Then it is a consistent estimator. As you can see, as you increase n, the variance of this y tilde goes to 0, right? Now you tell me, is it a consistent estimator? The answer is yes. Right? Y tilde is unbiased, variance disappears as the sample size increases. So it is consistent. So this weighted sample mean satisfies the first 2 criteria. For the efficiency, we have to compare it against something else. So we'll talk about this a little bit later. Okay? So that's example 1. Now, what is really interesting is example 2. So here, the definition of the estimator is this. Y check is equal to y1. So the idea is you draw a sample, you only look at the first observation and use it as your estimator. You basically throw away everything else. So there's a lot of waste and information in your sample, but this can be an estimator. Okay? That's why check. And the claim is so this is the claim in example 2. Now can you do it? Can you check these 2 claims? So expected value of y check is equal to the population mean. The variance of y check is sigma squared. So why is it true? E of y check is E of y1. And E of y1 is mu of y, right? By assumption. The variance of y check is variance of y1, which is sigma squared. Again, by assumption. Okay? So let me ask you the same questions. So y check is this very wasteful estimator. You use the first observation and throw away everything else. Is it an unbiased estimator? It is an unbiased estimator. So being an unbiased estimator is kind of easy. It's not hard. So y check is unbiased. Is it consistent? Why not? It is unbiased, but variance does not shrink. Right? It doesn't go to 0, even if you increase your sample size. So can you imagine why? Because you throw away everything else. Only keep the first observations. Don't even look at what information are there for the other observations. So even if you increase your sample size, you don't necessarily have more information in your estimate. That's why it is not consistent. Okay, so Y-check is unbiased, but it is not consistent because it doesn't go to 0. So, Y-check as an estimator is not such a good one because it failed to pass the second criteria. Is it okay? Do you follow me? Now let's take a look at example 3. Now here is our beloved sample mean, Y bar. So let's just repeat. Y bar is 1 over n. So what's the difference between Y tilde, the first one, and this one? This one treats everybody equally. Okay? So that's the difference. Now the claim is E of Y bar is equal to mu of Y. The variance of Y bar is this. Okay? Let me give you 30 seconds. Can you write it down why this is the case? You're not going to repeat it. So convince yourself that the expectation of Y bar is equal to the population mean, and the variance is sigma squared divided by n. Now, did you do it? Now, let me ask this question again. Is the sample mean Y bar unbiased? Yes. Is it consistent? Yes. So we have two estimators that pass the first two criteria, Y tilde and Y bar, right? So they are good so far. Then we have to use the third criteria. So which one is more efficient between Y bar and Y tilde? Why? Y bar has a smaller variance, right? So compared to the weighted sample mean, the unweighted sample mean, which treats everybody equally, is more efficient. So this is our preferred estimator for the population. Okay? So when you have several estimators, you simply compare their values. You can go actually further. In the textbook, there is a claim which says the sample mean is the blue. What's the blue? Best linear, unbiased estimator. So what does it mean? If you think about all the estimators that is unbiased, like Y tilde is unbiased, or Y1 is unbiased, or Y bar is unbiased, right? All the unbiased estimator that is linear in Y, linear in data. So for example, Y bar is just a linear combination of your data, right? So it's a linear estimator. So out of all the linear, unbiased estimator, the sample mean is the best, meaning that it has the smallest values. Okay, so that's one reason why we like to use the sample mean. Okay, so it is pretty good. Now, I just have one more comment. Now, is the sample mean better than the sample median? Then there's no such guarantee though. The problem is it is best out of all the linear unbiased estimates. The set of linear unbiased estimates is kind of very small. So it's not the best out of many, it's best out of a few. So for example, the sample median is not a linear estimator, it's a nonlinear estimator. So which one is better between the sample mean and sample median? It really depends on the question, okay? So, but anyway, this claim says that sample mean is at least has the smallest variance out of these candidates. Okay, so that's it for today. So when you come back on Tuesday, we're going to do the testing and confidence interval for chapter 3. So please take a look at the textbook.